Okay, so let's start to use the Henderson-Hasselbalch equation. Let's do it in the context of a problem we kind of started where we were dealing with what was the best acid-base system to come up with a pH of 4.30. I gave you two choices. It turned out that benzoic acid, which is HC7H5O2, and I checked that and that's correct, with an H out in front. Okay, that would be a better choice than chloroacetic acid for hitting this target pH. So now what we're going to do is we're going to do a more robust problem. So not only being able to identify the correct acid-base pair to use, but now to actually do some calculations associated with it. So what I'm giving you here is that the solution contains 1 mole of KC7H5O2. And what this problem is going to ask us to do is calculate how many moles of HC7H5O2 are needed. All right. So we're making a buffer with a Henderson-Hasselbalch equation, and we're asked for an unknown. Now, a couple things. Whenever we see this keyword buffer and it looks like you're having to do a calculation, it's asking you to calculate any of these variables, all right? The first thing you write down is a Henderson-Hasselbalch equation, all right? Calculations, buffer, always start here, right? It's an equation that has 1, 2, 3, 4 unknowns in it. And so we work through the information of the problem and we try to get everything into the correct spot, okay? So let's start to actually just kind of make our substitutions. Let's make sure we understand what is what here and that we can identify the correct symbol fitting into the correct spot. pH is given. This is always our target. So we're going to write this. Use a different color. We'll write this pH as 4.30. All right. From the last example that we did, right, on the very last video, we knew pKa for this acid, right? And that pKa was 4.19382. That was something that we already calculated on the last example, all right? Now, a couple things here, all right? A minus, so this is plus the log of A minus. A minus in this case, well, what is the conjugate base? I look here and I see, oh, there's my acid, that's my HA. And this gets really annoying to keep writing, so we can even just kind of leave it as HA if we want to, all right? The base, though, should be A minus, and I don't see A minus anywhere here, except we know how to identify a salt now. And this is a salt. It has a K out in front. We know that Ks are spectator ions. So even though we have 1 mole of K, C7H5O2, we know for the purposes of the Henderson-Hasselbalch equation that that's really like 1 mole of C7H5O2. Now here, this is not moles. This is molarity. Right, but you'll see problems from your book and in Chem 101 that give you moles instead. Right? You need to know how to kind of work both. But how does moles work inside here? Well, if you think about this in terms of what its units are, this would be moles of A minus per liter of solution. Down here, this guy, I'll do it in a different color, HA, would be moles of HA per liter of solution. And now here's the thing, the buffer is made, all right, the buffer is made in one container. It's one solution. So the liters of solution here and the liters of solutions here, they actually cancel each other out. So just to kind of make sure you understand, all right, sometimes you're given concentration information and you throw it in as we've been showing you. All right, you can be given mole information, and because the liters of solution cancel, it's completely okay. All right. Another way of writing this would have the moles of A minus here and the moles of HA there. So it's completely okay that we're not given a volume for our solution. We can go ahead and use this equation and this idea to plug in the information that we need. So in the top, once we cancel these out, and then simplify, it looks like I have moles of A on the top and moles of HA on the bottom. Well, moles of A minus, oh yep, I looked at the chemistry of that salt. That's going to be 1.00. Okay. Our unknown, right, it's an equation with 1, 2, 3, 4 possible unknowns. The only unknown we have are going to be the moles of HA. And so I'm going to call that my X. So we have this equation now that we can go ahead and solve. Every buffer problem is the same. You analyze it and you find where the unknown is, you set it up, and then you do the math. there's a couple things mathematically you want to pay attention to when you do enact simplifications for this equation. Sometimes you have to undo a log, and there are other times you have to undo a p, like from a pKa or a pH. Just make sure you understand what you're undoing as you do the math, okay? And I'll talk about that as we go here, okay? So what we're going to do to simplify this is let's just finish it with each other. We're going to go ahead and do a subtraction there, right? When we do a subtraction there, what I end up with is 0.10611799 is equal to the log of 1.00 moles over x. Looking at significant figures, two decimal places here, two decimal places here, doing a subtraction, so there'll be two decimal places here. Now, sometimes we're so used to undoing a p that at this point we introduce a negative sign that's not necessary, all right? All we have to do to try to isolate this x is we have to raise both sides as a power of 10. If you look at what we have to do for this problem, we have to get rid of the log. It's not getting rid of a p, it's getting rid of an log. How do you get rid of an log? You just use it as a superscript of 10 as an exponent of 10. Over here then what we get, 10 to the 0.1061799 in my calculator, give me 127,69679. All right. Over here, they just cancel each other out. They're inverse operations of each other. So you get 1.00 moles over x. Okay. Let's pay attention to significant figures here. All right. Two significant decimal places here, so two total significant figures there. We can solve this for x. When I solve this for x, I get 0.783105 moles. All right. This looks like we would have two significant figures in the answer. And so then my final answer is, okay, the moles of HC7H5O2 needed is 0.78 moles. So if we look down here to our original setup, all right, we could put the unrounded number in here to check, but it kind of makes sense. What do we see here? 1 and 0.78, those are kind of close. We have an acid and its conjugate together. We're fitting things into the Henderson-Hasselbalch equation appropriately. The final answer around to the correct number of significant figures is this 0.78 moles that we have right there. Okay? So again, the equation use isn't too bad. That's why I spent a couple videos just kind of getting down the idea of buffers. You guys are so used to solving for unknowns and equations that it's really, like I said, not something to be intimidated by, but you have to pay attention to details as always and make sure that you're getting the correct mathematical operations in the correct spot. Just for one other practice problem here. Let me set this up. Just to show you that any of those things in the Henderson-Hasselbalch equation can be an unknown, all right? So here's another example problem. A buffer is constructed. Constructed with 50.0 moles of A minus and 80.0 moles of HA. The pH is measured to be 9.17. What is Ka for HA? So we have a general acid HA. We're given some measurements. We're told, importantly, keyword identification, that we have a buffer. Okay? We have a buffer. We're going to have to calculate something. We're given moles. We're given a pH. We have to write the Henderson-Hasselbalch equation down as a starting point. Right? Now remember, right? Equivalent to this, what we just went over, and I'm going to write it down again just to really hammer it home. An equivalent expression is to use the moles of A minus on the top and the moles of HA on the bottom. Now, which is going to be better for this? Are we given molarity information or are we given mole information? Let's go ahead and use this version right here. So let's do our checklist. Let's see what we have, right? We're given a pH. We're given a moles of A minus. We're given a moles of HA. right? What we don't know is the pKa. And what are we trying to calculate? We're not trying to calculate the pKa. We're trying to calculate the Ka, but we do know the relationship between these two objects. So again, we do our normal equation thing. We do our checklist. 4 unknowns. We know 3 of them. 3 of them. Let's solve for the last one. Okay. So let's throw some numbers in here based off of the information given in the problem. Please check my work. These are new examples. If you see some issue with what I do, make sure you email me, and we can correct it as a group. Right. So for my pH, I have 9.17. My pKa is going to be my unknown. All right. Inside my LOG, the base information's on the top. We were given 50.0 moles of A minus, right? We were given 80 moles of HA. Those go on the bottom, right? This is math that you can all just plug into your calculator. So we get 9.17 looks like pKa, right? Minus 0.2041149, right? This will have 3 significant figures. We can now solve for pKa. The pKa, I have to subtract this from both sides. The pKa that I get is 9.37411. Oh, this must be a 9. 9. All right. It's not going to matter in terms of the answer, but I think that's a 9 back in the previous step. So now we have to solve for Ka. And here's where we have to pay attention to what we're undoing. How do we undo a P? We don't just use 10 to the on both sides. We're not undoing an LOG. We're undoing a P. We undo 10 to the minus, right? Whatever we're raising that power to. So just remember, it looks different than undoing an LOG. We include that negative sign. And so what I get for my final Ka here is I get 4.2 times 10 to the minus 10, right? So again, all right, it's all about just making sure you're paying attention to undoing LOGs versus undoing Ps, but really that's the main thing that you run into in terms of just making sure you're paying attention to all the little details that you need to get through a problem completely and to finish it off, right? This is how you use the Henderson-Hasselbalch equation. You fit the correct things into correct spots and you just follow from there, right? We have one more discussion to talk about with a slightly modified version of the Henderson-Hasselbalch equation, and we'll do that in our next video.